Welcome back, guys. In this video we are looking at the chain rule as it applies in application problems. Related rates come up a lot as an application of the chain rule. So we're going to work through two example problems, and we're going to focus primarily on what all of these quantities mean. So here's our example. It says, suppose that the temperature on a plate is given by this function. So temperature is a function of x and y, and it's given by this. I don't really know the units of this temperature, but every xy location on a plate has a certain temperature, and maybe this is our plate. And then we've got an ant. It's walking along a path on the plate, and the path is given by r of t equals sine of 2t times I hat plus cosine of t times j hat. And the path that's associated with that looks like this. And as t increases, I'm actually not 100% sure which way this goes. When t equals 0, we've got sine of 0 is 0, cosine of 0 is 1. And then when t equals pi over 2, we'll have sine of pi, which is 0, and cosine of pi, which is negative 1. So t equals 0, we're here. At t equals pi over 2, we're over here. Maybe we need to find out where we are at t equals pi over 4 to figure out how we're getting from that point to that point. But there should be arrows along this path to indicate the orientation. We'll fill those in a minute when we answer the other questions. So the first question says, what is the ant's temperature when t equals pi over 4? Well, that's actually pretty easy to find. At t equals pi over 4, that's a particular time, and r of t is a position vector. It tells us the location of the ant. So this is x of t and y of t. So if I want the ant's temperature at this time, well, I can do two things. First, I'll find the ant's location using my vector valued function r of t, and then once I have that location, I can substitute into my temperature function. So it's just like regular composition of functions, pre-calculus style. First we'll find the position at t equals pi over 4. So I'm thinking of this as position or location at t equals pi over 4. So I need x of pi over 4, y of pi over 4. So that's sine of 2 times pi over 4 is pi over 2. And then I've got cosine of pi over 4. Well, sine of pi over 2, or 90 degrees, is 1. Cosine of pi over 4 is square root of 2 over 2. So it's about 0.7. So when t equals pi over 4, we're at the location x equals 1, y equals about 1.4 divided by 2, or 0.7. So this should be out here, x equals 1, and at that time, t equals pi over 4, let's just say seconds so that we have some units, and we're going to be at that location. That's square root of 2 over 2 for y. So it looks like we're tracing out the curve in this direction. At least initially we're going from t equals 0 to t equals pi over 4, we're going that way. Okay. So that's our location, or our position at t equals pi over 4, but we weren't asked for position, we were asked for temperature. So what I do is I take my position, my x, y here, and I substitute it into my temperature function. So we find the temperature at that location. So we're evaluating t at 1 and square root of 2 over 2. So you have 5 times x squared times y plus 12 times x times y to the 5th. X is replaced with a 1. Y is replaced with the square root of 2 over 2. And then we simplify. So I end up with 5 root 2 over 2. And then we're adding 12 times square root of 2 divided by 2, all raised to the 5th power. Oh, I was hoping it would simplify it for me. It's not giving me an exact answer. It's giving me a decimal approximation of about 5.66. Let's say that that's in degrees Celsius, who knows? But that's a particular temperature. So at t equals pi over 4 seconds, we're at this location, and if the ant is at that location, it is experiencing this temperature of 5.66, let's say degrees. This question says find the ant's location at that time. Actually, we just did that. Maybe we should ask those questions in the opposite order. So we find x at pi over 4 and y at pi over 4. We already did that. We got 1 and square root of 2 over 2. I'll just write CA. Okay, so I know the temperature is this, our location is this, and we're given a particular time. So we've got a time that corresponds to a position, and that position corresponds to a temperature. Then the question says, how fast is the ant's temperature changing at that location? Anytime you see how fast, and this goes back to Calculus 1, you know you're looking for the rate of change of some quantity with respect to time. And then they're going to tell you what that quantity is. So they say, how fast is the ant's temperature changing? So I put those two pieces together, and I know that I'm looking for change in temperature with respect to time. Well, there are a couple of ways I can do this. I can either find temperature in terms of time by replacing x with sine of 2t and y with cosine of t, and then simplifying and then differentiating, or I can just use the chain rule. So let's practice using the chain rule. Since temperature depended on two variables, our chain rule will have two terms. We'll have the change in temperature as x changes. So if we're at this location, x changes by a little bit, the temperature is going to change due to that change in x. And then we'll multiply that by the derivative of x with respect to time. So it's how fast is that x changing every second. So this is giving us the change in temperature with respect to time as x changes, or let's say due to changes in x. So as x changes, the change in temperature with respect to time is going to be given by the change in temperature with respect to x times the change in x with respect to time. Now as y changes, we're also going to get a change in temperature, and that term looks like that. So this is the change in temperature with respect to time due to changes in y. Okay, so that's our chain rule, and that's what we need to evaluate if we want this dt, and it says at this location. And the location is associated with a few other things. So let's say we're given a particular time. At that time, we're at a location, which is given by the components of the vector valued function r of t. So this is x of pi over 2, or excuse me, pi over 4, y of pi over 4. I keep writing pi over 2, or thinking pi over 2, which happens to be 1 and square root of 2 over 2. And we know that the temperature at that time because of what we found earlier, or the temperature at that location, at that time, which occurs, and at that time we're at this location. The ant is experiencing a temperature of about 5.66 units, whatever those are, maybe degrees. Okay. So you want to keep all this in mind. How fast is the ant's temperature changing at that location? So this location is associated with this time, and the temperature is initially 5.66, let's say, degrees. Well, in order to find that change in temperature with respect to time, I need to use the chain rule. So I'm going to compute these two partials of t with respect to x and y first. And we can either find those partials of t with respect to x and y and substitute in the location, or we can find these with respect to x, or find these partials of t with respect to x and y, and then write them in terms of time and then substitute the time. Either way, we're talking about the same location. At this location, or the ant is at this location at this time, and it has this temperature. So there are lots of correct ways to do this. So let's compute these rates of change of temperature with respect to x and y, and then evaluate them at the location. So at x naught, y naught equals 1 and root 2 over 2. So we're just going to go through one step at a time. First step is to compute those rates of change. So we want the change in temperature with respect to x while holding y constant. So we're taking the partial with respect to x of this function, which is easy enough. I've got a constant times x squared. The derivative of a constant times x squared is just my constant, times the derivative of x squared with respect to x, that's 2x. 5 times 2 is 10, and then I've got an x times y right there. Over here, I've got the derivative with respect to x of a constant times x. The derivative of a constant times x is just my constant. So that's the partial of t with respect to x. So as we go 1 unit in the x direction, the temperature is going to change by this much. So at this particular location, the location of our ant, the change in temperature with respect to x is given by this. We've got 10 times our x value times our y value plus 12 times our y value raised to the 5th. So this simplifies to 5 root 2. Over here we're going to have 12, and square root of 2 to the 5th is square root of 2 times square root of 2, which is 2. It's 2 of them. Square root of 2 times square root of 2, it's another 2. That's 4 of them, and then there's going to be one more square root of 2. And then we've got 2 to the 5th in the denominator. So 2 times 2 times 2 times 2 times 2. And I know we're in Calculus 3, that's not necessary, but I just wanted you to see that 2 of these reduce with this. I'll take out a 4 here and reduce a 4 there. So we end up with 5 root 2 plus 3 root 2 over 2. So we've got 6.5 times square root of 2. 6.5 times square root of 2 is 13 root 2 over 2. Okay, what is that again? 13 root 2 over 2. That's approximately this much. So this is telling us that the temperature changes by about 9.19 units as we move 1 unit in the x direction from this location. X equals 1, y equals root 2 over 2. That's what would happen. Now I also need the partial of t with respect to y, and I need to evaluate that at that particular location. This is the derivative of a constant times y. The derivative of a constant times y is just our constant. Here I've got a constant times y to the fifth. So I bring my constant down, and the derivative of y to the fifth is 5y to the fourth. So I end up with 5x squared. 12 times 5 is 60. And that's the partial of t with respect to y. And if I want the partial of t with respect to y at that location, I'll have to substitute in the location to this function. So my partial of t with respect to y was 5x squared plus 60x y to the fourth. Make sure, yep. And then I want to evaluate that at the location 1 square root of 2 over 2. So I'm replacing x with 1. I'm replacing y with root 2 over 2. And we're raising that to the fourth power. So this ends up being 5 plus 60 times square root of 2 to the fourth is going to be 2 times 2. And then down here we'll have 4 2's. So 2 of those reduce with 2 of these. 4 goes into 60 15 times, and so we get 20. So temperature goes up by 20 units as we move 1 unit in the y direction from this location. Okay, so that's that. Now, in order to use the chain rule, we needed both of those partials of t with respect to x and y at that location, and then we also need to think about, or we also need to find the change in x with respect to t at that location, and there's a change in y with respect to t at that location. But remember, that location is associated with this time. So I just need those two derivatives evaluated at this particular time of pi over 4 units, maybe seconds. Okay, so let's compute x prime at pi over 4 and y prime at pi over 4, excuse me. So x is, let me look at my notes, x is sine of 2t, y is cosine of t. The derivative of x with respect to t is derivative of sine. Derivative of sine of something is cosine of that something times the derivative of the inside by the chain rule. And then the derivative of cosine is negative sine. Make sure you have that angle inside. All trig functions need angles. Now we want to evaluate this at the particular location, and we already found out that location was associated with the time t equals pi over 4. So these two pieces together imply that x at t equals pi over 4 is given by this, and y prime, I said x, but it's x prime at pi over 4 is given by this, and y prime at pi over 4 is given by this. Well, this simplifies to cosine of pi over 2. Cosine of pi over 2 is 0. 2 times 0 is 0. And sine of pi over 4 is square root of 2 over 2. So we're going to get a negative 1 times square root of 2 over 2. So we've got our two derivatives of x and y with respect to t. We've got our partials of the temperature with respect to x and y. We just multiply all of those guys together to find the change in temperature with respect to time. So I need to substitute my change in temperature with respect to x and y, those partials, into the formula, and I also need to substitute these derivatives of x and y with respect to t into the formula and simplify. So we've got this. Dt dt is partial of t with respect to x times dx dt plus the partial of t with respect to y times dy dt. And the partial of t with respect to x, don't remember what that was, but we can look it up. We'll flip a page over. Partial of t with respect to x was calculated down here. We have 13 root 2 over 2. Partial of t with respect to y was 20. Dx dt is 0 at that time. And dy dt is negative square root of 2 over 2. So we end up with negative 20 root 2, or negative 10 root 2, excuse me. And root 2 is about 1.4. So we're going to see negative 10 times square root of 2. It's about negative 14.14 units. What does that mean? Well, let's say temperature is in degrees and time is in seconds. I'm going to say this is degree per second, given those units. So that means our temperature is decreasing by 14.4 degrees, 14.14 degrees every second when the ant is at this location. That's our location. So r of t equals pi over 2 is pointing right there. Keep saying pi over 2. I meant pi over 4. It's telling you that's where our ant is located. At that time, the ant is at that location, and its temperature is about 5.66. Well, according to our calculations, 1 second later, the temperature is going to be like 14 units less than that. So let's add 5.66 to this. So 1 second later, the temperature is going to be negative 8.48 degrees, if these temperatures were measured in degrees. So that's an application of the chain rule. Now, if you want to, you don't have to use this form. You could also use the gradient evaluated at this point, dotted with r prime of t, and you get exactly the same answer. So let's just write that in that alternate notation. So this is just another method for doing exactly the same thing. It says, compute the gradient of temperature and evaluate that at x of t naught and y of t naught. And then dot that with r prime of t naught. Well, x of t naught and y of t naught, that's x at t equals pi over 4 and y at t equals pi over 4. And this is r prime at pi over 4. Well, this is just the vector. It's t evaluated at that location, and that location we calculated earlier was 1 square root of 2 over 2. So we're evaluating our partials at 1 and root 2 over 2. And we're dotting that with r prime evaluated at pi over 4. Well, our partials were, let me see. Partial with respect to x was 10xy plus 12y to the 5th. Partial with respect to y is right here, 5x squared plus 60 xy to the 4th. And we evaluate that at 1 and root 2 over 2. And then we're dotting that with r prime. It has components x prime and y prime, and x prime was 2 cosine of 2t. Y prime was negative sine of t. And we'll evaluate this at t equals pi over 4. Well, when I substitute in 1 and root 2 over 2 here, it turns out that the value I get for this is 13 root 2 over 2, and the value I get for this is 20. When I substitute t equals pi over 4 here, I get 0 and negative square root of 2 over 2. And then when I take the dot product, I've got 3 root 2 over 2 times 0 plus 20 times negative root 2 over 2. So we still get negative 20 or negative 10 root 2, or approximately negative 14.4. Let's say we're temperatures in degrees and our time is in seconds. So we get exactly the same answer, it's just we come about it a slightly different way. I like this notation, it's very compact. It tells me what to do. Compute the gradient, evaluate it at the point. Compute the velocity vector, evaluated at the particular time that is associated with that point. Take a dot product. Or you could do it this way. This is also a very nice way to handle it. So you compute the two partials and evaluate them at the point. Isn't that exactly what we did when we calculated the gradient and we plugged in the point? It's just a shorthand way of doing the same thing. Or then we can compute x prime and y prime at pi over 4. It's just like computing r prime and then substituting in pi over 4. So now I've got this vector that represents all of that, the x prime and y prime at pi over 4. And this vector, the gradient, which represents the partial of t with respect to x and the partial of t with respect to y at that particular location that's associated with that particular time. Then we take the dot product and we get the same answer. So you can do this if you like. You don't have to, though. You can do it the other way if you prefer as well. Okay, so let's do one more example. Got a word problem. We're told that the radius of a right circular cone is increasing at a rate of 1.8 inches per second. So I've got a cone. And its radius, it's at the bottom here, is increasing at a rate of 1.8 inches per second. So it's just getting larger. The radius is getting larger and larger. Every second it's 1.8 inches larger. While its height is decreasing at a rate of 2.5 inches per second. This is its height. And dH/dt, they told us it was decreasing at this rate. So that's negative 2.5 inches per second. Now, I probably went a little fast there. Let me go through this problem statement again. The first thing I started doing when I read this problem statement was I saw that I'm dealing with a right circular cone. So you want to draw the picture of the right circular cone. And then I started talking about the radius and the height. So I labeled the radius down here and the height here. Now, whenever they start talking about rates, then you know that they're giving you derivatives. So we have to translate the English sentences that are written here into something that looks like a formula, some relationship between variables. So this says the radius of a right circular cone is increasing at this rate of 1.8 inches per second. So it says the radius is increasing at a rate of 1.8 inches per second. So when it says rate and it's talking about the radius changing at that rate or increasing at that rate, and increasing is another key word that I need, then I know that they're talking about the derivative of the radius, and you might say, with respect to what? Rates of change, it could be the change in radius with respect to lots of different things. To figure out what it's with respect to, you look at the units of this guy right here. They're telling us the change, we're looking at the rate of change of the radius, and it's increasing, so that means it's positive, at a rate of 1.8 inches per second. When I see this per second, I know that this is a time change. This is how the radius is changing with respect to time. And I also know that radius is measured in inches because they give us this inches per second. So that is dr, because it's talking about change in the radius, per unit time, so dt. It's 1.8 inches per second. Then let's look at the rest of the sentence. It says its height is decreasing, so it's negative. decreasing at a rate. So the derivative of the height this time is a negative value, and it's 2 inches every second. So that height is getting smaller and smaller. Every second it loses another 2.5 inches. So I write that down. Then the question says, at what rate is the volume of the cone changing? So at what rate? So they're asking us for a derivative of volume. So I have to translate this question into mathematics. I need to know, what are they asking me for in terms of the variables in my problem? So at what rate is the volume changing when the radius is 120 inches and the height is 140 inches? Okay, so that's the question. Well, I think this is a related rates problem, and the chain rule from Calculus 3 is appropriate because volume doesn't just depend on time. Volume depends on height and the radius. Now, this would have to be given to you. I wouldn't expect you to know the volume of a cone, but it turns out that the volume of a cone, a right circular cone like this, is 1/3 pi r squared times the height. Now, I could take the derivative of both sides of this with respect to time using implicit differentiation, like it was a Calculus 1 problem. But now that we know the Calculus 3 chain rule, we can find the derivative of volume with respect to time just using that Calculus 3 chain rule. So I've got my equation, or it will be given to you, and I can use my equation and the fact that volume depends on r and h to state my Calculus 3 chain rule. For the derivative of volume with respect to time. Well, the radius is changing with time and the height is changing with time. So, and we have the volume as a function of two variables, the radius and the height. So our chain rule is going to have two terms. The volume is going to change due to changes in the radius at this rate. So this is change in volume with respect to time due to changes in the radius. And then I need to add to that the change in volume with respect to height due to changes in the height. Or excuse me, the change in volume with respect to time due to changes with the height. Okay, and this is asking for dv dt, so we want all of our answers finally in terms of time, and actually they're giving us a particular radius and a particular height, so we should be able to write this as a single number rather than a function of t. So it's actually pretty easy to compute. We just need those two partials and those two first, those derivatives of r and h with respect to time. And actually those were constant and given to us, so we're just going to substitute those in at the end. Okay, so let's talk about how we approach problems like this. First, I take my sentence, my paragraph here, and I pick it apart. I will draw a picture and then read these sentences very carefully. And I try to translate every English sentence into some equation or some statement involving my variables. So they start talking about a right circular cone, so I draw it. That's a good approach. I'm going to say sketch the situation because it's going to vary from problem to problem. Sketch it if appropriate. Label the appropriate variables. And then you want to translate the English sentences that are given to you into mathematical equations. I guess I would say, are all equations mathematical? Well, I guess we have equations in chemistry too. And that's for another course. So we translate the English sentences into equations, and then we translate the problem statement, the thing that they're asking for, I'm going to say translate that problem statement or question into a variable form. So I know I'm looking for the rate, at what rate the volume is changing at this, when we have this particular radius and this particular height. But I needed to change that question into this in order to use math to answer the question. So we've done all of that. Then we state the appropriate chain rule. Given this particular equation. Now, if we weren't given the equation for volume, we would have to look that up. And then we just use the chain rule to answer the question. So I need these two partials with respect to, partials of v with respect to the radius and height, and then we're just going to substitute into our formula. And I'll use subscript notation. So I want those two partials when r equals 120 and h equals 140. And those are both in inches. Okay, so that's where we're at. Actually, I should put a line up here. So that was the question, and then this is us sketching a picture, translating English sentences into equations or statements involving our variables, the variables in the question, and then we're taking that question and translating it into a question that we can answer mathematically. Then we stated the appropriate formula of our volume, and then we stated the chain rule, and now we're going to use it to answer the question. Okay, so we're going to compute these two partial derivatives, this one and this one. So I need the change in v with respect to r, holding h constant. So this is how much is the volume changing as r increases by 1 unit. We want to know. Now if we're treating h as a constant, I've got 1/3 as a constant, pi as a constant, and h as a constant. I'm differentiating r squared with respect to r. So I pull out my constants, and the derivative of r squared with respect to r is just 2r. So I end up with 2/3 pi times r times h. Then I evaluate that at r equals 120, h equals 140. So I've got 2/3 times pi times my r times my h. That's 120 inches. This is 140 inches. And then I'll use my calculator to do the arithmetic. That's 2 times 120 times 140 divided by 3. So I get this amount, 11,200 pi. And it looks like inches squared, but be careful. It's not inches squared. This is change in volume with respect to the radius. Maybe I should write it this way. Change in v with respect to r, evaluated at 120, 140. So the units on this are the units of the numerator divided by the units of the denominator. It's just like slope. It's rate of change, but it's an instantaneous rate of change. At this particular radius and height, the instantaneous change in volume with respect to the radius is 11,200 pi units cubed. Now our radius and height are being measured in inches, so the volume is also going to be measured in inches times inches times inches, so inches cubed. So this is 11,200 pi inches cubed per inch. So for every 1 inch increase in the radius, the volume is increasing by this much. Okay, now I also want to calculate the change in volume with respect to height. So I take the partial with respect to height of 1/3 pi r squared times h. Now this is just a constant times h. The derivative of a constant times h is just my constant. And then I evaluate that at the particular radius and height that we were given. And again, I need the appropriate units. So I've got 120 cubed, or squared, excuse me, that I'm dividing by 3. So I get 4,800 pi. And these are units of volume per units of height. So this is inches cubed per inch. So for every 1 inch increase in height, the volume is increasing by 4,800 pi inches cubed when the radius is 120 inches and the height is 140 inches. That's what our rate of change of volume with respect to height is. Okay, so now we're going to add all those, or put these pieces into this formula and use it to calculate the change in volume with respect to time. So we computed those partials with respect to the radius and height. Now we're going to substitute into our formula. Of course, we're going to simplify our answer and then interpret our answer. Interpretation is really important in Calculus 3. It's really important in all of your math classes, but it's particularly important in Calculus 3 because the calculations themselves aren't that difficult. These are very simple derivatives, but the concepts are important. So we've got dv dt is the partial of v with respect to r times dr dt plus the partial of v with respect to h times dh dt. And the partial of v with respect to r we calculated. That was 11,200 pi inches cubed per inch. We're going to multiply that by the change in r with respect to the radius. So there's not quite enough room. And then we're going to take, so I'm substituting that in. So that is right here. And then I'm taking the change in volume with respect to height, and I'll substitute that in. 4,800 pi inches cubed per inch. That goes here. Okay? And now I need to multiply by the change in the radius with respect to time and the change in height with respect to time. Change in radius with respect to time, well, that was given to us. They told us the radius is changing at 1.8 inches per second. So I substitute that in. And the height is dropping at 2.5 inches per second. I know that that's very small, so I'm going to write it a little bit bigger. Notice that the inches reduce here, and I end up with a change in volume per second due to a change in the radius. So I end up with 11,200 pi times 1.8 inches cubed per second. And then I've got 4,800 pi, times negative 2.5, and those inches reduce, also inches cubed per second. I'm going to calculate these, 11,200 times 1.8. And I think I will multiply by pi this time, get an approximation, just so that we have a better sense of what's going on. That calculator is always good about giving me the exact answer. So I'll put this button here, gives me the decimal approximation. So we have about 63,334.5. inches cubed per second. So if the height was staying constant and the radius was increasing at 1.8 inches per second, then the volume would increase by 63,334.5 inches cubed per second due to that change in the radius alone. Now, that's not what's happening. The radius is changing, it's increasing. Simultaneously, the height is decreasing at negative 2.5 inches per second. So let's see how that height shrinking changes the volume. So we'll take our 4,800, multiply it by negative 2.5, multiply that by pi, get a decimal approximation. So I've got negative 37,699.1 inches cubed per second. So we're losing 37,699 inches cubed every second due to that height shrinking at 2.5 inches per second. Well, the question is, well, what's the total change in volume with respect to time? The radius is increasing, the height is decreasing. Well, what happens? We'll end up with this minus this. And this is an approximation. I get this number plus that negative number from before, and it gave me about 25,635.4 inches cubed per second. That's our change in volume with respect to time due to changes in the radius and height at a particular value of r and h, when r is 120 inches and the height is 140 inches. So we've answered their question. All right, guys, that's it for applications of the chain rule. You might see something like this. I love temperature on a plate, temperature on a cone. It's often the case that something depends on position like this. Call this a scalar field. Every xy is associated with a particular temperature. And then we want to know, well, from the experience of the ant, that temperature is changing every second as it moves along this curve. The ant is just walking around, seeing what's going on here in the xy plane along its curve. From the experience of the ant, that temperature is changing. How is it changing? How fast is that temperature changing? Well, we can use the chain rule to figure that out. We can also answer traditional related rates problems, looks like a Calculus 1 problem, using the multivariable chain rules that we've studied. A little bit simpler than we did in Calculus 1. In Calculus 1, this would be a more complicated problem because we didn't know about those partials of r, v with respect to r and h yet at that point. So now these are much simpler.